Our next chapter is image restoration and reconstruction and geometric transformations. In this, we are going to start with a model of image degradation or restoration process. The degradation process is modeled as a degradation function that, together with an additive noise term, operates on an input image, that is f of x, y, to produce a degraded image, that is g of x, y, and the equation comes out to be g of x, y equals to h of f of x, y plus n of x, y, where h is the degradation function and n of x, y is the additive noise term. Given g of x, y, some knowledge about the degradation function, that is h, and some knowledge about the additive noise term, that is n of x, y, the objective of restoration is to obtain an estimate f cap of x, y of the original image. The estimate comes out as close as possible to the original input image. In general, the more you know about h and n of x, y, the closer f cap of x, y will be to f of x, y. If h is a linear spatially invariant process, it can be shown that the degraded image is given in the spatial domain by the equation g of x, y equals to h of x, y convolution f of x, y plus n of x, y, where h of x, y is the spatial representation of the degradation function. Frequency domain representation of a degraded image is given by an equation capital G of u, v equals to capital H of u, v into capital F of u, v plus n of u, v, where the terms in capital letters are the Fourier transforms of the corresponding terms in the spatial domain. The degradation function capital F of u, v sometimes is called the optical transfer function, that is OTF, a term derived from the Fourier analysis of optical systems. In the spatial domain, small h of x, y is referred to as the point spread function, that is PSF, a term that arises from letting h of x, y operate on a point of light to obtain the characteristics of the degradation for any type of the input. The OTF and PSF are a Fourier transform pair, and the toolbox provides two functions, that is OTF to PSF and PSF to OTF, for converting between them. Next is noise models. Now, how to add noise in a model? So, the image processing toolbox uses function imNoise to corrupt an image with noise. This function has the basic syntax as shown here. G equals to imNoise, f, type, parameters included in parentheses, where f is the input image. Next is generating spatial random noise with the specified distribution. So for this, spatial noise values are random numbers characterized by a probability density function PDF or cumulative distribution function CDF. Random number with Rayleigh CDF is generated by using the expression R equals to A plus square root of B into log of 1 minus rand m, n. Next is periodic noise. Periodic noise is in an image arises typically from electrical or electromechanical interference during image acquisition. So periodic noise is typically handled in an image by filtering in the frequency domain. The model of periodic noise is a 2D sinusoid with the equation shown below. Next is estimating noise parameters. Function stat moments computes the mean and central moments up to order n and returns them in row vector v. Because the moment of order 0 is always 1 and the moment of order 1 is always 0, stat moments ignores these two moments. The syntax is shown below, that is v, u and v in square brackets equals to stat moments p, n in curly parentheses, where p is the histogram vector and n is the number of moments to compute. Often, Noise parameters must be estimated directly from a given noisy image or set of images. In this case, the approach is to select a region in an image with the featureless a background as possible so that the variability of intensity values in the region will be due primarily to noise. To select a region of interest in MATLAB, function ROI poly is used, which generates a polygonal ROI, where ROI is region of interest. This function has the basic syntax as B equals to ROI poly f, c, r included in parentheses, where f is the image of interest and c and r are vectors of corresponding column and row coordinates of the vertices of the polygon. To obtain the binary image and a list of polygon vertices, you can use the syntax as b, c, r in square bracket equals to ROI poly and dash 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 in parentheses. So, the right side of this equation indicates any valid syntax form for this function, and as before, C and R are the column and row coordinates of the vertices. This format is particularly useful when the ROI is specified interactively because it gives the coordinates of the polygon vertices for use in other programs or for later duplication of the same ROI, that is region of interest. Next is spatial noise filters. The function spfilt performs filtering in the spatial domain with any of the filters having syntax f equals to spfilt, and in parentheses write g, type, m, n, parameters. The linear combination of the inputs can be computed by using the function imlincomb having syntax b equals to imlincomb, and in parentheses include c1, a1, c2, a2 up to ck, ak. Next is adaptive spatial filters. Spatial filters are applied to an image without considering the changes in image characteristics from one location to another. The results can be improved by using filters capable of adapting their behavior depending on the characteristics of the image in the area being filtered. Let us consider an adaptive median filter having subimage S of xy centered at location x, y, minimum intensity value zmin in sxy, maximum intensity value, that is zmax in sxy, median of the intensity values zmed in sxy, and intensity values zxy at coordinates x, y. There are two levels in which the adaptive median filtering algorithm works. First is level A. In this, conditions comes out to be if zmin is less than zmed is less than zmax, then go to level B. Else, increase the window size. If window size is less than equals to S max, repeat level A, else output as Zmed. Or level B includes if Zmin is less than Zxy less than Zmax, then output gives out to be Zxy, else output is Zmed. The command ADP median is used to implement this algorithm having syntax f equals to ADP median and in parentheses write g, s max. Next is modeling the degradation function. The typical approach to determine the nature of the degradation in the image is to experiment by generating PSFs and testing the results with various restoration algorithms. Another approach is mathematical modeling of PSF. Moreover, blind deconvolution can be used to infer the PSF with no information of PSF is available. PSFs can be modeled by using IM filter and PECIAL functions. Image blur is one of the degradations encountered in restoration problems. Image blur can be modeled by using fspatial function as PSF equals to fspatial, and in parentheses include motion, comma, alien, comma, theta. This call to F special returns a PSF that approximates the effects of linear motion of a camera by alien pixels. Parameter theta is in degrees measured with respect to the positive horizontal axis in a counterclockwise direction. The default values of alien and theta are 9 and 0 respectively. These settings correspond to motion of 9 pixels in the horizontal direction. Function imFilter is used to create a degraded image with the PSF that is either known or is computed by using the method as described. G equals to imFilter and in parentheses write F comma PSF comma circular, where circular is used to reduce border effects. You then complete the degraded image model by adding noise as G equals to G plus noise, where noise is a random noise image of the same size as G. Function checkerboard is used to generate the test pattern, which is useful in comparing using same image or test pattern having syntax C equals to checkerboard and in parentheses write NP, M, N, where NP is the number of pixels on the side of each square, M is the number of rows and N is the number of columns. If N is omitted, it defaults to M. If both M and N are omitted, a square checkerboard with 8 squares on the side is generated. If in addition NP is omitted, it defaults to 10 pixels. The light squares on the left half of the checkerboard are white. The light squares on the right half of checkerboard are grey. Next is Wiener filtering. Function dconv WNR is used to implement Wiener filtering in IPT. There are 3 syntax forms for the same. First is fr equals to dconv WNR and in parentheses include G, PSF. Second is fr equals to dconv WNR and in parentheses include an extra parameter that is NSPR. Assumes that the noise to signal power ratio is known either as a constant or as an array. The function accepts either one. This is the syntax used to implement the parametric Wiener filter, in which case NSPR would be a scalar input. The final syntax is fr equals to dconv WNR and in parentheses included an extra FACORR parameter. In this assumes that autocorrelation functions NACORR and FACORR of the noise and undegraded image are known. This form of dconv WNR uses the autocorrelation of N and F instead of the power spectrum of these functions. If the restored image exhibits ringing introduced by the discrete Fourier transform used in the algorithm, it helps sometimes to use function edge taper prior to calling dconv WNR. The syntax is J equals to edge taper and in parentheses include I, PSF. This function blurs the edges of the input image I using the point spread function that is PSF. The output image J is the weighted sum of I and its blurred version. The weighting array determined by the autocorrelation function of PSF makes J equal to I in its central region and equal to blurred version of I near the edges. Next is constrained least square or regularized filtering. Another well-established approach to linear restoration is constrained least squares filtering called regularized filtering. Function dconv REG is used to implement constrained least squares filtering in IPT, which is having a general syntax as fr equals to dconv REG and in parentheses write G, PSF, noise power, range, where G is the corrupted image, fr is the restored image, noise power is actually proportional to n modulus squares, and range is the range of values where algorithm is limited to look for a solution for gamma. If the discrete Fourier transform introduces ringing in the restored image function, Edge taper is used prior to calling deconv reg to blur the edges of the input image, which is having a general syntax as j equals to edge taper, and in parentheses include I comma psf as before. Next is iterative nonlinear restoration using the Lucy-Richardson algorithm. Function deconvolucy is used to implement LR algorithm in IPT, which is having a general syntax as fr equals to deconvolucy, and in parentheses write g comma psf comma numit comma damper comma weight, where f is the restored image, g is the degraded image, psf is the point spread function, numit is the number of iterations and its default value is 10, damper is a scalar that specifies the threshold deviation of the resulting image from image G, and weight is an array of the same size as G that assigns a weight to each pixel to reflect its quality. Next is geometric spatial transformation. Geometric transformations modify the spatial relationships between pixels in an image. The image can be made larger or smaller. It can be rotated, shifted, or otherwise stretched in a variety of ways. Geometric transformations are used to create thumbnail views, adapt digital video from one playback resolution to another, correct distortions caused by viewing geometry, and align multiple images of the same scene or object. The image processing toolbox represents geometric coordinate transformations using a so-called T-form structure, which is created using function makeItForm. The calling function for makeItForm is T-form equals to makeItForm, and in parentheses include transform type, parameters, and so on. The first argument transform type is one of the following strings, that is affine, projective, custom, box, or composite. Additional arguments depend on the transform type. Spatial transformations can be applied to an image either by using forward mapping or inverse mapping. The function imTransform uses inverse mapping, which is having a syntax g equals to imTransform, and in parentheses include f, tform, interp. Next is image registration. Image registration methods align two images of the same scene. IPT supports image registration based on the use of control points, also known as tie points. IPT functions CP2T form can be used to fit a specified type of spatial transformation after choosing a sufficient number of control points. The toolbox includes a GUI for the interactive selection of control points on a pair of images. Transformation types supported by CP2T form and makeItForm are shown here, that is affine, box, composite, custom, linear conformal, and LWM. So you can go through these tables by yourself by pausing the video here. Other transformation types that are supported by CP2T form and makeItForm are piecewise linear, polynomial, and projective. So these are the basically 9 transformation types that are supported by CP2T form and makeItForm in image registration process. So you can pause your video here and go through these 9 types by yourself. So this is all included in this chapter. Next we are going to start with color image processing. So this is all. Thanks.